Bismillahirrahmanirrahim. Assalamu alaikum, dear students. In today's lecture, we are going to talk about the C compilation process. For this purpose, I will be using the all-time famous GNU GCC compiler, which is used to compile C, C++, Objective-C, Objective-C++ languages. We will try to peep behind the curtain and see what actually is being done in the four phases of C compilation process, that is, the pre-processing, compiling, assembling, and linking. To understand the concepts completely, we will use tools like readelf, object dump, OD, NM, the Linux linker LD, and LDD, which is used to display the shared object dependencies in a program. Hope today's section will be informative for you all. Let's start playing. Well, who am I? I'm Arif, and the name of my machine is also Arif. My present working directory is in my home directory GCC, and in that EX1. Before we proceed, let us talk a bit about the theory. What is a compiler? Students, compiler is a program that transforms source code of a high-level language to the underlying machine code. And the underlying machine can be x86, Motorola, PowerPC, ARM, Spark, Cell, or MIPS. There are various examples of the compilers that are available in the market. We'll be talking about GCC. The other on the BSD is CLang. We have the Turbo C compiler, Visual C++ Express as well. Well, GNU compiler is an integrated distribution of compilers for major programming languages like C, C++, Objective-C, Objective-C++, Java, Fortran. And of course, GCC can be set to cross-compile. By cross-compile, I mean a compiler that can generate machine code for a platform other than the one in which it is running. So GCC can make use of tools like AutoConf, AutoMake, and libtool to generate code for some other architectures as well on which it is running. Well, right now my host is the Mac OS EXI Capitan, on which I'm having 1.6 gigahertz Intel Core i5 processor. For the virtual environment, I'm using Oracle VirtualBox 5.0.26, and on it I have created 64-bit machine which is running Ubuntu 16.04, and the kernel is 4.2.0, and this is probably an older version. The latest that came in is July or August 2016 is 4.7, and in some later videos we will talk about how we can upgrade the Linux kernel of the operating system on which we are running. So let's get back to work. So GCC version, the version of the GCC is 5.4, and as far as the standard C library, the version of standard C library is 2.23. LDD is something that we're going to talk about a little bit later. Once again, the library is also a bit old, 2.23. Right now it is 2.24, which came just 10 or 15 days back. So let's start doing some practical work. So let's see, what is this? This is a C program, the standard C program, the header file, the main, and the famous printf statement. We can compile this program using GCC hello.c. It has generated an executable with the name of a.out. We can execute this executable, and it has successfully executed. Similarly, we can do the compilation of a C++ program as well. This is a C++ program. This is always a Greek line for many of the first year students. Right. So, as far as namespace is concerned, gentlemen, namespace is a region of code. It is a technique of naming that region and referring to that region of code with a name. You can create your own namespaces, but the standard namespace that is available to you by the C++ library is named as std. And instead of writing std colon colon operator over here with this symbol cout and cin and many other symbols that are available, you use the keywords using and namespace. So using namespace std over here makes you free that you don't have to write things over here. Okay, anyway. So to compile a G++ program, we use G++, and you see we have the a.out, so we are done. So we are going to talk about the C compilation process. C++ is a similar one. So the first ambiguity which comes to my students' mind is why we are using dot forward slash. If we use a.out, it says command not found. So the reason of this is right now the shell which is running, it is searching for the executable named a.out in all those directories where the path variable is looking. So let me see the value of the path variable over here. So this path is a shell environment variable which contains colon separated list of absolute path names of the locations where this shell is going to search for the executables. And right now my executable is located in home, Arif, GCC, EX1 and C, which is of course not over here. So let me add this path in my path directory. Let me use the variable $pwd. So this says that add to this variable whatever is there already in this variable, and then you should place the path of the current working directory. So if I see path now I have the location of the present working directory over here as well. So now if I write a.out without a dot forward slash, that will be executed because the shell will search for an executable named a.out in this location, then in this, then this, then this, and finally it will find it over here. But it is always recommended never to add the present working directory path in your path variables. It's always better not to do that. Once we'll be talking about some further hacking, probably I will be able to explain it a little better. So let's get into a bit of more details by taking another example. Well, as far as compilation is concerned, the C compilation process, if we go behind the curtain, try to peep behind the curtain, we will see that there are four major phases. Let me see if I have the slides running showing you the phases. Okay, fine. There are four major phases: the preprocessor, compiler, assembler, and linker. Let me briefly go through theoretically and then we will try and execute all this step by step. In the first step, the pre-processing phase, the GCC takes hello.c and generates a file hello.i. Right now we have seen that GCC takes hello.c and creates a file a.out. Actually it performs all the four stages, and finally creates a dot out. But if I want GCC to just do the pre-processing phase and not the remaining three phases, I give it the -e option. And if I give -e option, it generates the pre-processed file with the extension of .i and throws it to stdout. And over here I have done the output redirection and place it in a file hello.i. And what preprocessor actually do is it interprets the preprocessor directives, the hash include, it include the header files, it remove all the comments which you have given in your code, and it expand the macros if there are any. So let me do this. GCC -e .c, and if I press enter, you see it's all spread over here. And if I want to do this, so I have the hello.i file. I can view the contents of this hello.i file, and you can see there are a lot of code which I have of course not written in it. These are different symbols which have been added, different data types which I can later use, and of course at the end this is these are the 2 or 3 lines which I have written in this file. So this is what is known as pre-processing. I'm sorry for moving around. Fine. After pre-processing, what is done is the compiling. The compiler basically checks for syntax errors. If no syntax errors, the expanded code is converted into assembly code, and that assembly code is the one which is the underlying hardware. And to tell the compiler to perform just these two phases, we can input this .c file, give -s option, and it will generate the .s file. Or we may give the .i file and it will generate the .s file. Let's go back over here again and see how this can generate the .i and .c file. Wow, the file is not there. I need to see the .s files. Do I have it over here? I don't have it. GCC -s probably, it's capital S, hello.c ls. Okay, sorry, it was a typo. It is not lower s, it is capital S. So if you see this, the contents of this file now, this is the assembly code that it has generated. So once again, after pre-processing, the .i file is created. After compiling, the .s file is created, and that contains the assembly of the particular architecture. And if you see, this seems quite familiar to you if you have gone through the assembly language course. This is Intel assembly, but it is of course not in the Intel style, it is in the AT&T style. We'll talk about it in some other video. Okay, so the third phase is of course the assembling phase. In the assembling phase, what we do is we give -c option to the C compiler, and you give hello.c file or the .s file, and it generates the .o files. What the assembling process does is it converts the assembly language code to the machine dependent opcode. Now we are going to convert our code to the x86 code. Each object file, we have only one .c or only one .o file. There is a table that is known as symbol table, which contains the name, type, and relative addresses of the global variables, name and relative addresses of functions defined in this program, of course, and the name of the external functions like printf. For example, we have used printf in this .c files which have not been defined by us, defined somewhere else. These symbols are all mentioned in this .o file. And finally, let me finish it up, the linking phase. The linker links a collection of object modules and libraries as input and combines them to produce a single executable. If we have more than one .c file, the linker actually combine all those .o files to a single file and name it a.out. We will see how we can link multiple .c files after 5 or 10 minutes. So it takes a symbol table of all the .o files and create a global symbol table that can be used by the executable. And in case of single source file, it links appropriate functions like over here the printf. And we will also see in detail that how this printf is linked with this executable and what are the options of static and dynamic linking that are available to us. Okay, fine. So let me give you a shortcut. You can give -save -temps option to hello.c. This will tell GCC to create all the temporary files and not delete them in between. So once you press enter and C, it will generate the .i, the pre-processed file, the .x containing the assembly code, .o containing the object code, and finally the executable, the linked file a.out, which you can execute. Okay. Now we have seen the contents of .i, we have seen the contents of .s. It contains the pre-processed code. This contains the assembly code. Let's see the contents of .o. Okay, let me get it. Oops. Okay, fine. We cannot see the contents of the .o files. Let me see the type of this file. Okay, file is a command that is used to tell you about the type of a file. So we come to know that hello.o is not a text file. It is an ELF 64-bit LSB relocatable x86 64-bit version for System 5, and it is not stripped. A lot of information. So this .o file is in ELF format. This format is used for storing programs or fragments of programs on disk in System 5 Unix or Linux systems. Other than the .o files, the final executables are also basically in the same format. And there are core dump files and .so files that are also in the same format. But anyway, coming back to the point, we want to read the contents of this object file. So there is a program read ELF. So this program basically helps you read the contents of the .o as well as the executable files. You can in your own time look at the details, the platter of information as far as the ELF format is concerned. You can see that, but right now let us try to read the headers, the program headers of our a.out program. Oops. So there are a lot of program headers. So you see this ELF file type is an executable. So let's see the program header of hello.o. So it says there are no program headers in this file. So program headers reside only in the executable file. -h option is used to see the file headers. So these are the standard file headers, and of course these file headers are there in the .o file as well as on the executables. This is a magic number which is used to execute a file. The class is ELF64. Data is tools complement little endian on my machine, and versions and a lot of information over here. It tells you the size of these headers, the program headers, the section headers, and the symbol table as well. If you want to see the section headers, so we can use hyphen capital S option, I think. Okay, so hyphen capital S tells you that there are 13 section headers. Some of them might be familiar to you, like the .text section. You can see the .data as well, which contained initialized global data, and the .bss section, which contains the uninitialized data, block started by symbol, and you can also see the sim table over somewhere here. And if you want to see the symbols, so small s, these are probably the symbols that are used in this .o files, and the main are of course main and protest, which is used by the main. Anyway, so read ELF is one of the options that you can use to dig inside your executables and object files. There is another command that is od object dump. This command dump files in octal and other formats. You can use this as well to see the dump. For example, if I want to see the octal dump actually of hello.o, so this is the octal dump of the entire executable file. So you can see this is octal. By default, od do the octal dump, and if you want to see the hex dump, so you place an -h over here. This is the hex dump, and there are a lot of other options as well, which you can find out on the man page of od, of course. There is another command that is obj dump. This command is used to again display information about the object files. So how to do that? The most important part that this command do is to disassemble. Let's suppose hello.o. So you see, isn't it familiar to you? Well, details of these will be covered somewhere later when we'll talk about the probably depth of the assembly language in using net-wide assembler and probably using the GDB and maybe sometimes in buffer overflow. But anyways, what we have done right now is we have been able to see the .o files, the object files and the ELF files using read ELF command, the octal dump command, and the obj dump command. So these are the three commands that we have used to view the contents of these files. And naturally, we have seen that we cannot see the contents of this file using the standard programs like less, more, head, tail, and cat. So the final stage is the linking stage. Remember, gentlemen, the a.out is the finally linked file. I penned this topic for another 5 minutes, and let's talk about the multi-file programs, and then we'll come back to the linking process again. Okay. So fine. This is just a hello world program for containing multiple files. So we have prog1.c. So this is my driver program, which is using a2l function, ASCII to long, which is of course there in stdlib.h, a2l, which is there in stdlib.h, no problem. This program is getting two command line arguments. The first one is going in X, the second one is going in Y, and of course the very first one, which is rv sub 0, is the name of the program, and right now I don't need that. There are four other symbols: myadd, mysub, mymul, and mydiv. These four symbols are actually the function names, which are nowhere in this driver program. However, there is a file mymath.h which is telling this program that these symbols are there somewhere and will be used later, but it will tell the compiler to pre-process, to compile and to assemble. That is to generate the .o file of this. If I don't write my math.h over here, the, the, the compilation process will give me error that these symbols are not found. So let me show you the code of my math.h. It just contains the function declaration of these, and my add.c is containing just the definition of my add function. My sub.c contains definition of this. My div.c contains the definition of the division. I've avoided division by 0 error, and my mul.c contains definition of this. Fine. So we have my add.c, my div.c, my mul.c, and my sub.c containing the definition of add, div, mul, and sub respectively. My math.h containing the declaration of all these four functions, and prog1.c is actually the driver program. Let me remove this .o file. Fine. So let me compile. Let me compile all the .c files. All the .c files. I'm saying compile all the .c files over here with a -c option. I'm telling GCC, please carry out the first three stages: pre-processing, compiling, and assembling, and give me uh, my add.o, my div.o, my mul.o, my sub.o, and prog1.o. I need 5.o files. Once I press enter, I get an error that says my math.h is not found. Actually, this my math.h is written in the angle brackets. This has to be written in the double quotes. If it is written in the double quotes, then the GCC will look for this file in the present working directory. But I have written it like this, so it will look for it in the standard location. And what is the standard location of the header files? These are located in, for C, they are located over here. You see, all the header files are over here, and you can see stdio.h as well, and you can see math.h as well. For C, they are located over here, and for C++, they are uh, located in 5 point something. This is a version. Uh, I just want to list this directory, so you can see for this G++, the header files are located on my machine over here, and you can see, of course, the IO stream and I stream and O stream and I1 IP and etc. etc. Anyway, so what has been happening is that we have got an error because the compiler is looking for this header files in the standard location. So what we can do is either we can copy this to /usr/include, or we can tell the compiler that compiler, please look for the include files in the present working directory. This dot means the present working directory. You can write $pwd over here as well. And it is asking for an option. So this is an option, so we need to place an I. So you see we have the 5.o files over here. Now the pre-processing, compiling, and assembling has been done. Now is the linking time. So to link, what we need to do is I need to tell that my add.o, my sub.o, my mul.o, my div.o, prog1.o, these files should be linked to create a single executable. Once I press enter, this executable will be created with the name of a.out. I can always say link all the .o files in the present working directory. a.out is created. And another important option that normally one must use is the -o option to GCC, which tells GCC to create the executable with the name of, not with the name of a.out, but with some other name. Let's suppose Kakamana. So now the executable name is Kakamana, Kakamana, Kakamana. So this command is again not found. Why it is not found? Sorry. It is not found because our home Arif GCC multi-file is not there in the path variable. So we need to use // again. So one way is path is equal to $path. Sorry, let me write it in capitals. Dot. So now wherever we go, the present working directory will be in the path variable. So let me export it so that the shells which are spawned by this shell later on also contains the new value of the path variable. So if we see, we have dot over here. Now Kakamana will work, and you see we have a code dump. Oh, Kakamana is actually expecting two command line arguments, two numbers, and these numbers are added and subtracted and multiplied and divided. Okay, fine. So this is working. Once again, let me sum up the multi-file concept. We have a lot of .c files. We create the .o files, and finally we link all those .o files together. Fine. One question that still arises is, what about this my add symbol, my sub symbol, my mul symbol, my diff symbol? These symbols are there in these .o files, my mul.o, my diff.o, and so on. But what about A to L symbol? And what about this printf symbol? What to do with these symbols? These symbols are not there in anywhere in my source files. I need to find out. Probably one may say that these are there in the standard C library. So let's move on to our next example. Okay, fine. The next example here is going to talk about the linking process in detail. We will see what we mean by linking. So over here we are seeing that this program is again going to take two command line arguments. One is uh, a float or a double type of argument, A2F I have used instead of A2L, and the other is also a double type of argument. I have used str2f. This is a better, newer version of converting a string to a double value, and then I'm going to pass this to the power function POW, and finally I'm displaying the results. So remember, these two are there in stdlib.h. They are declared there, so successfully compilation will be done. POW is there in math.h. This symbol is declared in math.h. So compilation will be done. There will be no problem as far as the compilation is concerned. So let me do the compilation. -c power.c. By compilation I mean pre-processing, compiling, and assembling. So power.o has been generated. But remember, it still do not have the code for A2F, str2f, POW, and printf. It can contain only if it will be linked with the required libraries. So let me say power.o hyphen o myXE. What I'm saying is that this power.o should be converted to myXE and should be linked with the required libraries. So I've got an error. Amazingly, the error is only on the POW function, not on A2F or str2f functions. That means that only this function is not available. So remember, A2F, str2f, printf, these are the functions which are there in the standard C library, and the standard C library contains all these files. So that's why we are not getting the error. And every program, GCC links every program with the standard C library. But if you want to link your program with the math library, you have to write something over here, like -lm. You see? So what is this lm? I will talk about it after a while. But however, this myXE has been created. myXE, enter first number 2, enter second number 4. So it's created. So I don't know. I think that they should get it in the command line arguments. Let me do again. GCC power.c -o myxc hyphen lm ls myxc. Okay, so fine, beautiful, dot forward slash myxc. You see, now the issue is that in my file system somewhere probably my exe file is living over here as well, and my exe file is living in some other directory as well. And since I have done a lot of things with my path variables, so it is executing this my exe file from somewhere else, not this one. So if I want to execute this my exe file, I need to use like this. You see? So remember, it is never a good practice to add the present working directory name in your path variable, and it is never good to add so many directories in your path variables where you can have a lot of exe files and you can have name conflicts over there. Anyway, so let's talk about the libraries now. The location of the libraries, the location of the standard C libraries are USR lib x86 64 Linux GNU. This is the location of most of the libraries. So you can find most of the libraries over here. See, a lot of libraries, a lot of .so and .a files. Let me grab. Grab what? Uh, let me grab this lib c.so. You see, this is the standard C library. The location of the standard C library is usr lib blah 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 and libc.so, and there is another version libc.a. So this is the dynamic version of the standard C library. This is the static version of the standard C library, and they both are available at this location. When I say GCC automatically links to the dynamic library. If this is not available, only then GCC will go for the static version. Another thing, the naming convention. Whenever you say, suppose what we have done before, to the GCC compiler, I am saying that you need to link with the standard C library, so I will use -lc. You remove this lib portion from here and you remove this .so portion from here. So this is the name of the library you're going to use with the -l option. So -lc. If you want to use the math library, the name of the math library is libm.so and libm.c. You can see that using the same command. So let me write it. ls usr lib x86. Let me pipe this to grep libm.so. You see? And similarly, we have the .a version of this as well available. So it is not necessary that your library should have just a single character name. There are libraries which have longer names like the libpthread library. Anyway, so once again, power.c is a file which contains code which is there in the math library as well as which is there in the library of the standard C library, libc. So we can do power.c -lm, enter. Remember, you don't have to explicitly link with the standard C library because uh, no program can be compiled without that. So GCC implicitly places a C over here even if you don't link it. So this is errored out. Let me statically compile it. So we have a static a.out as well. let's see the sizes, the difference in sizes of these two files. You see, the size of the executable which is dynamically linked is just 8.6K, and the size of the file which is statically linked is 1.1 M, because the file which is statically linked contains the entire code of POW, printf, str2f, a2f. That is why its size is huge. While the linker has not linked the has not placed the code of these 3, 4, 5 functions in this. It has just placed a stub over here, and it will do that once once it is loaded or once it is there in the memory to be executed. There are a lot of advantages of using static libraries over dynamic libraries and vice versa. We inshallah will discuss these in some later video, and we'll be talking about creating our own static and dynamic libraries and using them inshallah. However, and then let me use another command which I've used before, LDD. Let me say what LDD is. So LDD is used for to print shared objects, so shared libraries which are used by your executables. So I say LDD a dot out. Let me do it for the static a dot out as well. It says it's not a dynamic executable, which we know that. And let me use LDD on a dot out. It says that this is linked with libm.so. This is linked with libc.so. This is something which you will see on every editor out, and this is linked with this this the standard linker LD, and this is also linked with VDSO. So these two are a little bit new to you. So let me talk about the VDSO. VDSO. Let me man it for you. Man VDSO. So you see. So it is virtual dynamic shared object. It's a virtual dynamic shared object. It is a small shared library that Linux kernel maps into the address space of all the user space applications. So you will find this in all user space applications. And again, some of the time when we will talk about strace utility, we will see what this actually do. And finally, LD. So let me say man LD as well. Remember, always do LD, always do man whenever you are in ambiguity. So LD is basically the GNU linker. So that means if I have a program, let's suppose power.o, I can link it to the libraries using LD as well. So let me do LD power.o and -o my new exe. Oops. So this time you see GCC doesn't give you error on these symbols. It just gives you error on POW symbol. But LD requires you that you need to link it with the standard C library. Once we have linked with the standard C library, we don't have these three errors. We just have the POW error, and we need to link with the oh sorry, we need to link with the math library as well. Once we do this, we just get an error that is cannot find start symbol underscore start to this address. Actually, GCC starts its execution from a symbol called main, which is of course there whenever you compile it, and LD is habitual of finding out the symbol known as underscore start from which it starts its execution. So it is not found, but even then you can see the my exe has been created, my new exe which we have just created, and to power okay, sorry, I need to do like this. My new exe, my new exe, why it's not working? It says my new exe no such file or directory. Okay, let me do this again for you. LD And instead of giving this, let ld created with the name of a.out, it has created. Okay, fine. So it is not executing this, probably due to the same reason which I have talked about. So better is that we use GCC for doing this. Power.c hyphen lc and hyphen lm, and probably this lc is not required with GCC, and this time the a.out has been created, and of course it has work. Fine. So that is all for today. Let me sum up briefly and very quickly. I have talked about basics of a compiler. We talked about the cross compilers, and we have moved on to GCC. What GCC do? We have seen a Hello World program using GCC. We have seen that where are the standard C header files located, USR include, and we have seen in depth behind the curtain the four stages, uh, creating the intermediate files using different options to GCC, and doing it at once using the hyphen safe hyphen temps option. We have seen what the preprocessor do, what the compiler do, what the assembler do, and what the linker do. We have seen that we can watch files, the contents of the pre-processed files, that is the .i files using less, more, head, tail, cat. We can see them in the .s file as well, which contains the assembly, but we cannot see the files that are .o files or the final executables. For that, we have seen different tools like readelf, uh, and we have seen the obj dump. We have seen the OD command, and finally we have again seen that how the libraries are linked with your files. The important thing is the standard C library, libc.so is implicitly linked. You don't have to explicitly link it, but the math library or any other library has to be explicitly linked. And we have also seen that once you statically link your executable, its size is too big, and otherwise it's dynamically linked and its size is small. And there are a lot of merits and demerits of both. And finally, we have seen the LDD as well, which tells you about the different dynamic libraries with which your program is linked. Uh, and the bonus is NM, which says the symbols. It displays all the symbols that your executable has. And if I run it on power.o, that will be more reasonable to you. Power.o contains A to F main, POW, printf, and str2f. These are the external symbols that are there in this file. Gentlemen, hope this lecture was informative to you all, and I hope that if you have any query, you can mail me to arif@pucit.edu.pk. You can give comments and you can give suggestions to improve. Of course, I have learned a lot from my students, and I am still learning. I wish you all the best. Allah Hafiz.